Okay. Hi. Hi, Bob.
Hi, how
Nice
are
to meet
you?
you. Hey, good. Hey, my name's Callie. We're the UTSA team.
Yes. I was just looking
Um,
at your poster session here today, and we've got a bit of time to because there's nothing following us on this channel that I'm aware of. Well, we might get booted off, but we've got a bit of time as need be. Um, but what I wanted to do is maybe ask a few questions about your design that I had after reviewing both your final report and your poster session, and also maybe give you a chance to ask any questions that you might have as well. I know you've had kind of a challenging year, as everybody has, with COVID, and it's really impacted, I think, in a lot of ways, some of your project, whether it relates to the payload delivery or whether it's even related to the completion of your airframe and things along those lines. So, and I know that you're a novice team too, so you got a steep learning curve. You're probably, hopefully you're roped up, and protecting each other that way. So I guess I'd like to explore a little bit more about your choice of using kind of STEM teams to kind of do your payload work. I realize it's kind of like outsourcing some of that work is kind of maybe just from a pure effort perspective, that's helpful. It's also really nice to think about helping STEM teams, bridging them into kind of rocket engineering and things along those lines. Could you talk a little bit more about that? I know you probably have some regrets that you didn't end up having to throw a bulk plate payload, in the front end of your rocket because of that program. How would you do that differently if you chose to kind of outsource the payload next time?
well, I think it was a pretty valuable experience for us and also for the high school team as well. Initially, when we thought about outsourcing the project to one of our alumni's high school who has a rocket team, um, we thought that they were going to be more impacted than they ended up being by the whole COVID lockdown situation. But it turns out that they had just as much schoolwork as they would have had normally, and they worked on their own rocket project in addition to this payload project. So it being a third party payload project in their eyes, and not one of their first party projects, it obviously did not end up winning out in the end. As far as something that I would do differently is we tried to be very hands off. We tried to sort of model it after a competition like NASA SL or SAC, and just have them schedule everything on their own. But I think they got a little overwhelmed and just wanted to live high school lives, which I understand that.
Yeah, well, yeah, we all kind of want to live just college lives or even old fart lives like mine too. So, I can appreciate that. I think, you have to, it's kind of a fine line you walk. I kind of appreciated the kind of the novelty of trying to source this to STEM and kind of getting them into the track. That's like one kind of judge's view. Another kind of judge's view is like, well, they just decided to skip out on all the innovation around the payload.
Yeah.
And so you have to kind of be aware of maybe some of those kinds of decisions. And the reason I'm saying that is, like, if you look at rocket design from like a top-down perspective, right? There's an awful lot of trade-offs involved. And you start at the top saying, okay, what's the mission? Land on Mars. Okay. What are the kind of the physical characteristics of the rocket? Okay, well, we're going to borrow from last year's design, but we need to make some changes for things that could be improved. And then what's the cost and effort involved? So you see, that's kind of like the high level trade-off. It's like, why do you choose carbon fiber? Well, maybe that's another layer down in this kind of analysis. Why do you choose a fin plan of XYZ, right? That's even another layer down, right? So but at the highest level, you have to start with what your mission is. And so if you're outsourcing something like the payload, you really haven't got that high level kind of design point, right? Maybe it's okay. So maybe you can abstract and say, okay, it's going to be 8.8 pounds and I really don't care what it is. But, but some judging and some ways of viewing kind of the whole rocket engineering kind of approach is indeed that you've got a very specific mission in mind, and so that's something to think about I'm probably a little softer than other judges might be in this area, because I like the idea of getting high schoolers, and I mean, I do mentoring with kids and all that kind of stuff too. So I appreciate that kind of a perspective, but something to be aware of maybe next year, as because what you really need to be driving, and I realize you're really novice in as a team and as a group in many ways, despite having a good kind of rocket culture in your area. You know, you want to move more and more towards just raw innovation in almost every aspect of your rocket design. Payload, your own laminations for nose cones and fin cans, novel kinds of ways of doing attachment of the various body parts, and novel ways. There's all sorts of good examples for some of this if you've had a chance to view some of the podium sessions over the past day and a half, right? So that's just a little bit of feedback. There is that there's some consequences, I think, of punting payload design, and it comes back and bites you hard when that team doesn't deliver, right?
We learned that for sure.
You'll learn it. And it's like, okay, so what am I going to do next time? It's kind of the lessons learned. So that's a really good kind of introspective on the lessons learned after you've had a chance to sit on it all summer. There's probably things that you could do differently, in my opinion, around how you manage the project. Kids who are 17 or 18 in high school need, whether they like to admit it or not, they need a lot of supervision. They're not quite ready to kind of take the tiller in many cases, right? There's exceptions, of course, but
yeah.
I was wondering, so another thing I noted in your reports is really there's mostly an absence of a lot of, say, graphical analysis, right? I don't think I've seen a flight profile like a rock sim flight profile, for example, right?
We didn't include one of those in the technical report. We included a screenshot of our open rocket file, and we also had a little graphic of the the flight profile.
Well, you had the ConOps.
Yeah.
So I think that kind of there's other analysis that is also being done on rockets of this size and seriousness, right? So I know you looking at your fin can construction and going with your 8-ounce, carbon fiber tip to tip and all that. Those are all great measures. There's a lot of teams that actually did actual fin flutter analysis and included those data, right, and informed their fin selection based on that data, right, and what their expected speed was going to be. As a matter of fact, when I was doing flight safety reviews on another team earlier this year, I pointed out that their fins are just too big. They're like the size of a duck wing, and they're gonna get ripped off at Mach 0.3, right? And so, I didn't actually tell them that. I said, you need to kind of go do some analysis on this, and then that comes, well, where do I get the software? Well, you don't actually. You kind of have to do it from first principles, because it's really hard to find the software, right? That kind of thing. So I'm wondering, one thing I felt that you were a little shy on in your reports is really kind of those analyses and the graphical data that kind of supports some of that. We've got teams that are doing, CFD on their rockets and, all of these things to kind of understand exactly what the drag profile is. So if you're thinking in the future about becoming more competitive in this space, it's almost like you have to up your game just a little bit. And I realize it's a walk, run, sprint kind of exercise that we're in right now. But one of the things when you're thinking about lessons learned is to kind of look ahead and say, what are we going to do different next year? And while you're doing that, I'd encourage you to think about how to get more into SRAD componentry, whether it's motors, whether it's your own layups, whatever the case may be. Okay, just food for thought. I don't know, does that make any sense?
Yes, sir. Yeah. I'll just take the blame for that right there. I did fin flutter calculations using, they have a list of the Baromet equations and a diagram on Apogee Rocket's website. There's a nice page on it.
Okay.
So I did fin flutter calculations. Unfortunately, I do not have them anymore.
Oh, No, that's unfortunate.
That's my fault.
Yeah. No, the fin flight, I use the same. Well, I started in a different location and I've modified. I've got my own calculators in that particular space. So actually, during some safety reviews on previous teams, I was kind of doing the analysis in the background and kind of going, you know, that's not the, you're missing something there. So you see, that kind of analysis would be really good, because part of the thing that we're trying to do in these reports is validation of the rocket. And one thing that you've suffered from is the inability to fly the rocket, because it's really not complete, right? And so you haven't got the test flight. You don't have as much kind of testing data and or analysis data to support the integrity of the rocket, right? I believe it would fly, but one thing you really need to do is to prove it, right? If you were going to go after like being a level 3 certified flyer, which you're all perfectly capable of starting to go down that path if you haven't already started going down that path, you'll understand exactly what I mean when you start having discussions with your TAPs, right? Because they're looking for that kind of information before they sign off on your design and allow you to fly with a leash on, right? And so those are kinds of things to think about, right?
We actually augmented our schedule a little bit whenever the competition went virtual, and we have a launch coming up planned for next Saturday, the 26th.
Oh, good for you.
So we actually kind of augmented our schedule, which I realize now that you're mentioning this may have been a little bit of a disadvantage since, you know, poster session materials and all the other materials were due like a week and a half ago. So we did, and especially in like the video challenge and the introduction of the team members and the description of our rocket, it was incomplete, but it's you can see it in the background of Adam's camera right there. We've been hard at work on it, getting it.
Well, he's got paint on it.
Yeah, that's about it. No. Just joking.
It looks like you're still doing some layup work on your fins. Or is that just an artifact of
the fins are actually complete, but we do have a chrome vinyl layup on the leading and trailing edges.
Oh, to keep it from peeling and stuff like that, right? Yeah. Oh, very nice. Yeah, it's a nice looking rocket. I like the design. Yeah.
Thank you.
Why? So, Adam, why did you choose Bluetube?
So the reason why Bluetube was the choice for our team mainly was from a cost perspective. Our team doesn't necessarily. We had a pretty tight budget.
Yeah.
I'll put it that way. And Tally could definitely expand more about that if you would like. But we had a tight budget, so Bluetube just seemed really to fit. And with that also, we didn't necessarily have the experience or I guess you could say the tools to work with fiberglass tubes and materials as easily. And it was also because of our past experience with Bluetube. Last year we participated in NASA student launch, and that rocket was constructed from Bluetube.
Was that 2-stage as well?
No, that was a single stage.
Yeah, that's I think, you know, I've flown Bluetube, and I've also flown others like Quantum and things like that, and I've had some of them unroll like a toilet paper roll. You know, they just, you know, they separate. So a lot of people are actually end up putting additional laminations and adding weight to the rocket. I almost exclusively use fiberglass these days, unless I'm doing a minimum diameter with carbon fiber or something. I was just kind of curious about the Bluetube, because it does have a reputation for being not nearly as strong, and I'm concerned about buckling, particularly around your stage joinery. You know, even though you've got 5 inches of overlap on your couplers and things along those lines, and there's a lot of thrust, and you have a lot of mass above it. So, you know, it's not like you're throwing an upper airframe that's got maybe 8 pounds in it. You're throwing, you know, an upper rocket that's, you know, also 30, 35 pounds. And, you know, so I think it'd be really, back to the analysis comment, right? Buckling analysis around critical joints, particularly in multi-stage rockets, is probably indicated, right? That because you need to kind of prove that stuff out. I realized you got tip detection and a couple of other things in place. That wasn't actually obvious until I was looking at your poster session in reading your final report. It's like, what are you doing to make sure that the rocket is actually pointing up and not sideways when that igniter goes off for your sustainer, right? But also, you know, just making sure that's just the analysis around that separation. How clean is that happening? Those are kind of things, particularly when you get into multi-stage, that you really have to be kind of conscious of, in my opinion. I know you've probably thought about it. I don't know if you have any comments on that.
I'll just say, yeah, Jim. Oh, sorry. Go ahead, Adam.
In that regard, that's why we made I completely understand from an analytical perspective that we should analyze those things, but at the moment, in the thought process of stiffening up those joints was that's why we decided to not only add a single bulkhead at the bottom of our couplers, but we added 2 additional internal bulkheads to provide some sort of additional rigidity within those sections of tube. And specifically on the inner stage coupler, we decided that it would be worthwhile to line the internal coupler with carbon fiber to provide that extra stiffness and to prevent any failure of the tube.
Yeah, so the coupler is probably really stiff, right? And I think you're using plywood, like 1/2 inch and 3/4 inch plywood for the inner and outer couplers, right? So that's probably really good for the coupler. I'm more concerned about maybe tear out of the Bluetooth of the airframe or the fin can itself, and I can be easily proven that that's not an issue. But I think that'd be really helpful to kind of prove as part of your analysis that's not an issue. Maybe it's just bend testing of a similar joint to kind of, on a it's like on a bench press or whatever. Is there what can you do to kind of validate kind of that the Bluetooth is actually as rigid as you think it is, even given a really stiff kind of avionics coupler, right? Food for thought.
Yeah, no, for sure. Thank you for that comment.
Yeah, no worries. So one thing, Tally, I think you made an error on in your poster session, and maybe I'll ask you about this, is you actually said that there was a combined initial and combined average thrust of the motors. That was the sum of the 2 motors, right?
Yes, sir. I think I probably did make that.
If I'm not mistaken, one motor is fired at a very different time than the other motor. Right?
Oh, that's true. Yeah.
Okay. So those are kind of little errors. Okay, ding. Okay, you get that one. So yeah, be careful how you use numbers. There's liars, damn liars, and statisticians. So you got to be careful how you use numbers. Sometimes it's easy to kind of get yourself fouled up there. I think the other kind of subtle details that I would really benefit from, because I didn't have like the ORC files or whatever you used for construction on the rocket, is information on things like rail buttons and shear pins, right? And what else do I have here? And motor retention. Those are kind of details. You really have to make sure that you communicate what the motor retention scheme is. Otherwise, you're dropping motor casings on people from space, right? And so, and rail buttons, normally I wouldn't have as much concern, because if you were flying at Spaceport America, they do basically a launch rail test. You put the rocket on the rail and it's got to support itself on the buttons, right? And if it doesn't, guess what? You're back to your shed to kind of figure out how you're going to recover from that, right? So in the absence of a test, I've got no way to judge basically the integrity of that kind of avionics component. Okay, so those kinds of details are the kinds of details that you're typically going to have to deal with in getting a level 3 cert or judging in general. We're looking for kind of attention to some of those details. Okay, does that make sense? And I realize that you're going to be and have been reusing previous rockets and previous analysis and test flights from the previous year. As you're thinking about next year's submissions and report submissions, don't be ashamed or don't be shy about sharing that flight data as part of the proof of your current design, right? With the caveat that, I think about like SpaceX reusing launch vehicles, right? I really wonder what their inspection process is when they make a go, no-go decision on reusing that launch vehicle.
Yeah.
Right? And every time you kind of come in hard, after about 10 flights, you probably are not getting many more flights out of an airframe. I don't care. There's always something. If you land on a rock as opposed to a piece of the sand or something like that, right? There's all these little micro fractures that occur. So at some particular point, if you've got an awful lot of reuse going on, the discussion becomes, well, how do you know that reuse of that component is a safe and wise thing to do? Okay, so that's something to think about as you start shaping kind of your reports for next year, right? Is how do you kind of really flesh out this validation? How do you validate and prove that your decisions were sound? How do you, augment lack of flight data, for example, if it's a brand new airframe, with analysis, that's a little more rigorous and things along those lines. It's just part of the crawl, walk, run, sprint kind of thing that we all go through as we, evolve into, sending things up 100,000 feet or something like that, right?
True. Yeah.
Any questions for me?
Well, I mean, I'll just make a statement. We were a pretty lean team this year.
Is it just the three of you?
It's three of us, and then there's three other people who regularly helped out in the project.
Yeah, I think I saw the 3+3 on your authors list on your final report. Okay.
Yeah, two of the other people really mainly just helped out once construction time came around. So yeah, for planning and design, it was Adam, Gabe, myself, and another guy named Patrick, who could not be here today. It was mainly us four. Yeah, we really tried on our club's Discord server, because we had a lot of members pay in this year to join the club, but it was just the whole long distance separation this year. Trying to keep people involved was a little bit.
It's really hard to build rockets as a group when you can't actually meet. Yeah, or share the same shop, and maybe you can, or you feel comfortable doing that, but it's still the notion of being able to expand your community. It's really tough. The fact that you stuck with your work here this year is really commendable, because it's been very tough for everybody. We lost over half the teams, between the ones that were accepted and the ones that are here at the finish line, right?
Yeah, we really did want to prove, because last year when we did NASA SL, it was also canceled at the last minute. So our rocket, we ended up building and test flying our rocket, but we never actually finished it off, painting it and all that. So we actually wanted to prove that we could finish something this year.
Yeah.
So yeah.
I fly so many rockets that are fiberglass green. I don't paint them until after I've got a bump on them, and even then my painting is lousy. Well, there's one back there. Anything else, Tally?
No, not from me, sir.
How about you, Gabe? I haven't heard from you yet.
I was kind of just thinking the same thing as Tally, that we did have like a really good start at the beginning. We had a lot of involvement. It kind of like slowly like trickled down a bit to the few of us that have been left. I was wondering if you had any like input or suggestions on I guess keeping involvement during this time. I know that we're going to be able to hopefully like get more involved in the coming time, but I was wondering if you had any suggestions or anything that you think we could have done to help with that.
I don't know how you do it. That's it's almost a cultural issue. It's I don't know how you do it. I mean, you only get so much out of social media, to the ability to collaborate. And people spend too much time probably staring at a computer already, right? And You know,
Yeah.
building things and getting out of your head is actually a really good way of team building.
I
You know,
know
I used to climb big mountains like in the Himalayas and stuff like that, right? And before you go on these trips, people are really, really argumentative and opinionated on what needs to be brought and how they're going to do this, that, and the other, and finally say, let's put this shit away for a bit and go get on a rope and remind each other that that there's something that we love to do besides plan, you know, and argue, right? And so it's really hard, and it's been just so tough this year to do anything involving collaboration. Even this conference has been fraught with peril in terms of, you know, running things on schedule and not stepping on each other's, you know, Zoom meetings and all of these kinds of things. It's just tough. So I know, I guess I don't. All I can wish for is that things improve to the point where this becomes less of a concern and we can actually get together more often. And then it's just getting down and building, you know. So if you spend too much time analyzing before you actually start building things, you know, that's kind of tough too, because you kind of death by analysis and then you don't have enough time, you know, to kind of finish the build. So trying to figure out how you kind of keep a steady mix of analyzing new problems and getting some work done, having something to look at that's evolving, that's always nice. But I haven't got a solution for COVID. I wish I did. Yeah.
I think one thing we also did was we kind of underestimated just the amount of equipment and materials that would go into this rocket. So we did kind of, we were a little late on getting our materials ordered earlier in the year.
Yeah, well, it's tough too, especially if you look at budgetary constraints, right? It's like you try to cut it pretty thin and you don't realize, you know, one missed cut and now I need to order another piece of tubing, right?
Yeah.
And your comment earlier about fiberglass, cutting fiberglass, yeah, a table saw works great, but what you really need is masks.
Yeah.
You know, and that kind of stuff, or an air cleaner, or, you know, a way to suck vapor out of the air. And it's the same thing with carbon fiber. You know, the fly, quote unquote, of carbon fiber is actually quite dangerous. You don't want to be breathing it. You don't even get it on your hands. It works its way into your skin, right? It's just hurts, you know, it's not going to kill you, but it hurts, right? So yeah, having a kind of a dust-free environment or an environment where you can do dust collection, and I don't find any real problems with working with fiberglass. The biggest problems I have with fiberglass is drilling holes in it, right? Because it all punches out on the backside, right? So you got to figure out how to kind of maybe use a coupler or something like that as an inner layer to kind of drill through the outer airframe, and but then if you're actually trying to drill for the couplers, then that causes a problem with the couplers too. So you got to come up with blanks. Maybe it's wood or something along those lines that you can stick in there to kind of provide a back end for the drill bit, right? But other than that, cutting fiberglass is not difficult. Sanding fiberglass is a little trickier. You ever seen grit sticks? Grit sticks are like
not sure I have.
Yeah, they're about a foot long, 1 inch wide, maybe 1/8 of an inch thick pieces of aluminum, and with sandpaper glued onto it. And they work really well for like putting a trailing edge on your fin, right? Nice straight edge, you know, and you're not cutting yourself if it's you know, carbon fiber, you know, you're using a stick, right? So there's certain tools like that help as you move into the fiberglass and carbon fiber kind of business. And then vacuum bagging, that's a whole nother thing, right? Because you really need to do vacuum bagging on any tip-to-tip layup, okay? There's two reasons, right? One is the strength of your composites goes way up as the amount of epoxy goes down. And so you're sucking all the excess epoxy out through kind of a layer. And then the other is it reduces the weight, right? So you're using minimal amount of epoxy, maximal fiber strength, right? So, but vacuum bagging is a bit of a trick. You need a compressor, you need a bunch of different things. So, you know, so the tools will continue to evolve, and try to figure out a way to save them, you know, keep them in your garage or whatever you need to do.
I think that was like going off of that is one big thing that we noted as a learning point for this competition is that we really want to try and build our like infrastructure as a club in terms of like, I guess stocking up on materials if budget allows it, so we can get building or testing as early as possible. I think that was something we kind of faced this year, that held us back a little bit. And so we really want to just like get like a storage on campus somehow, and so we can like have everything readily available to us, rather than waiting on shipping times or like any mishaps with that.
Yeah, that'd be nice. You know, if the mechanical engineering group or aeronautics engineering, you know, had a closet somewhere for you, right? Or better yet, something with a concrete floor, and you know, in a basement level that you can run heavy machines in. So yeah, good luck with that. Yeah, let's try a rocket innovation center. You know. Anything else, Adam?
Well, I guess going off of how we were discussing that we are in fact a novice group. You know, admittedly going into this, we didn't exactly know what exactly we were getting ourselves into whenever it came to a two-stage rocket. We were very, very novice in that regard. And that's where I designed my level 2 high power certification rocket to mimic the exact rocket behind me, in order to try to like learn as much as possible before building this one. But with that, I know there's still a lot that we could learn, especially from analyzing things. Would you have any recommendations for us to help us be better prepared for the future in regards to possible like construction techniques or design techniques or anything in that regard?
You know, I've not done many multi-stage rockets, and then it's a bit of a trick. I mean, people just doing air start on clusters is a trick, right? I mean, you know, I liked kind of you did some double-headed ignition, right? For redundancy and things along those lines, and I liked your current limiting kind of approaches. There are some tricks that you've got up your sleeve that I think are novel and quite useful. I don't think there's anything wrong with kind of proving out like a two-stage design like the one behind you on a smaller rocket, just as long as everything's kind of proportional. You just kind of blow it up, right?
Yeah.
And so I think there's always, I guess I have a lot of questions about how to best separate the stages, right? As opposed to just using the thrust of the motor basically to blow the booster off.
So in our case, we're actually not using the thrust of the motor to separate it.
Yeah, you have charge separation in there. Right? And so what do you use? And I see there's some people that just blow the can off, or there's some people that just rely on drag separation, right?
So for our rocket, we got a lot of our inspiration from Jim Jarvis.
Yes.
Because we've been working closely with him on the design of this rocket. So we utilize essentially like a little taped up sealed packet of black powder. And it would be anywhere from 0.5 gram to 1 gram, that is placed in the volume between the top of the booster avionics and the actual bottom of the sustainer. That will then ensure if there is a drag separation, that's great. However, if there is not, then we would have that charge to separate it. And then to mitigate the risk of the motor possibly being affected by that charge, will utilize the cap that comes along with the motor, along with tape and some various other adhesives to ensure that nothing is affecting it in that regard.
Yeah, so the igniter doesn't get damaged or something like that from the BP charge. And other people have used CO2 to kind of avoid some of the, you know, because that's a pyrotechnic event when you use black powder. Is that enough to ignite your motor? Probably not. But, you know, those are the kinds of risk things to think about. And Jim's talented, so you've got a good mentor there. And the notion using a flat cake is good. because you're not going to get any twist as it's separating, right? You want it to kind of push off uniformly. Other people might use a piston design or something like that. That's another way to do it. So there's all sorts of different approaches there. And there's all sorts of different designs about like how late you're waiting a second, right? I think after separation, confirmation, whether it's a second, is that the intent, is to kind of maintain as much of the kind of terminal velocity on the first motor and then kick it up faster? Or if you're trying to stay away from Mach, does it make sense to coast for 15 seconds and then light the second one off? There's all that kind of analysis that's kind of interesting too, that may actually result in using a different set of motors.
Yeah.
There's things like that that you can always think through, because once you lose the booster, well, does that mean you have more or less coast on the sustainer, right? Because the MV squared M plays a big part, right?
Yeah.
So if you're using a dart for a sustainer, then yeah, that's good because you're losing the drag, right, as the sustainer goes. But if you're the same diameter like you are, does it make sense to kind of carry kind of the booster with you for the M part of MV squared, right, to take it as high as possible before you light the second one off? I don't know. There's all sorts. That's an interesting analysis to do. You know.
I never thought about looking at that.
That's a really good, I think, class of trade-off analysis for multi-stage. Is like, well, do you want to use the same size sustainer as the booster? Do you wait between separation and ignition of the sustainer? Are you trying to kind of maintain a fairly constant velocity, or are you trying to really kick it up?
Yeah.
Right? Because the smaller sustainer, if it's got smaller fins, it's going to be much less resistant, much more resistant to fin flutter, right? And so it's capable of taking a much higher, speed. So this is all part of. I mean, you're in complicated space with doing multi-stage.
Yeah.
So I commend you on kind of tackling this, because it's not an easy problem to solve, and it's really fun to watch two big motors going like that, know? Or three motors for that matter.
That's what we're hoping. Yeah, it's gonna be fun. Gonna be fun to watch.
There's your 30,000 foot shot. Yeah.
Yeah.
All right, gentlemen, I'm going to let you go. I've got other things I got to take care of this afternoon. It's been a pleasure talking with you, and it's nice to see the work that you're doing, and keep it up. And I'll look forward to kind of catching one of your flights one of these days.
Okay.
Yep.
Thank you.
Honor talking with you too. Thank you.
Yeah. Have a pleasant afternoon.
You too.
You as well.
Too.
Okay. Bye.